So there's a couple things that I've done to help you out a little bit and to make things a little bit less stressful. I have moved the lab that we were going to do next time to next term. So that means when we finish the lab today, you can finish your lab notebook and get it in by Friday or today if you've got all the other labs done. Okay? So that will alleviate a little bit. Remember that up through 6.4 is due next time in sapling and the quizzes. Okay? So I want to make sure that we try and get through as much as we can of the notes today so that we can finish the notes by Friday so you have everything that you need. Okay? We're doing a mini lab. It's just a real short lab. Probably take us 15 minutes, 10 minutes max. It's in here. So we're not even going back to the lab. Okay? Other than that, then we'll start next term. We'll do the 2 labs, and then all you'll have left is your 6.6, or actually 6.5 in sapling, I think, because there's only 5 in this one, right? And then we'll have quizzes and your pre-lab, or pre-test, and then you can do the test. Okay? Any questions with what's going on and what's due by Friday? Okay, so let's get our notes out. Whoops. And let's start with Avogadro's hypothesis. We talked about several different laws last time. I'm going to see what you can remember without looking at your notes. Tell me what the ideal gas law is. Ideally, you're not a... No? The actual law itself. What's the actual law itself? Ideally, you're not a... No. Say it louder, Brandy. You don't know? Ideally, you're not pervert. What was the law? PV equals nRT, pervert, okay? So that was the ideal gas law. From the ideal gas law, we got the combined gas law. What was the combined gas law? Say it, Landon. Do you remember it? The combined gas law? I put him on the spot. Anybody help him? Yeah?
Is it P1 V1 over T1?
P1 V1 divided by T1 equals P2 V2 divided by T2. And I put a little lyrical there because it helps me remember it. Okay, then we went to Boyle's law. Boyle's law held what constant? Think of PTV. What did it hold constant? Temperature. So if it held temperature constant, what was the law? We did the experiment last time. Okay, P1 V1 equals P2 V2. We get rid of temperature because temperature is constant, right? Okay, then we went to Charles' law. Think of Prince Charles. What was held constant?
Pressure.
Pressure. So if pressure is held constant, what's Charles' law? V1 divided by T1 equals V2 divided by T2. Okay, then we went to Gay-Lussac's. Gay-Lussac's. Okay, what was constant there? Volume was constant, so we end up with the law P1 divided by T1 equals P2 divided by T2. Then we went to Grandma's law, or Graham's law. What was Graham's law about? We did that last time too, that experiment. What was it about? Awkward silence. That's the one we did in the straw. What was it about? Yeah.
Like rate.
It was about the rate of how fast gases move. So we got rate A divided by rate B equals the square root of the mass of B divided by A. So they flipped from one side to the other. Rate A divided by rate B equals the square root of the mass of B divided by the mass of A. Then we went to Dalton's Duh law, and we used that last time too because we bubble gas through water. What was Dalton's Duh law about?
Pressures added together equal the pressure.
Yeah, all the pressures added together equal the total pressure. Duh, right? Okay, and we used it to find the pressure of the gas. So we took the pressure of the gas is equal to the pressure total minus the pressure of the water. So this is Avogadro's law, and Avogadro worked with volume and moles. So if we remember back to our original equation of the combined gas law, N was on the bottom. Remember that? And I said most of the time N is not there. Well, Avogadro kept N there and worked with just volume and moles, kept keeping pressure and temperature constant. Okay, pressure and temperature constant. So basically, if the number of moles increases, the volume increases. This is a duh, right? Okay, but he did find out how many molecules were there, and he found out at STP, standard temperature and pressure, the volume of 1 mole of a gas equals 22.4 liters. And so we add that to our mole map at the top, and we can go now from moles to volume and back. So 1 mole of any molecule or any atom, or not atom, any element would be 22.4 liters at standard temperature. So let's go through some problems because we need to have some more problems under our belt. Remember, as we go through problems, we want to make sure to pull out, because these are all story problems, and I hope you all have calculators. Do I need to get my calculators out? I forgot to get them out this morning. I'll go grab them real quick while you get yours out. So if you need to borrow one of mine, you can, because we're going to need them for later for lab, anyway, that mini lab. Okay, if you need a calculator, I'll just set them right here, because we're going to need them for lab later. Okay, let's go through this. Pressure exerted. So what am I trying to look for, it looks like? Pressure. So this is my question mark. P1 is question mark. Exerted by, oh, whenever they give me mole, what am I probably going to have? What law? I can stop right there and I know what law they're giving me. What? Pervnert. That's the one that had the N in it. Okay, of oxygen is confined to a volume, 500 milliliters. And a temperature, ooh, right away I know temperature I have to do what with? All gas laws must be in what temperature? Kelvin. How do I get to Kelvin? Plus 273.15, and I get Kelvin would be 293.15 K, no degree sign. Now, I need R. Does anybody remember what R is? R is a constant. If I don't remember what R is, it better be something that is on my 3x5 card. In R, it tells me what every single one of the variables in Pervnert need to be in. So my pressure needs to be in atmospheres. That's okay because I'm looking for it anyway. My N or my moles need to be in moles. They are in moles. My volume needs to be in liters. Oh, it's not in liters. What do I need to do to fix it to go to liters? Do a little quick conversion here. There's 1,000 milliliters in 1 liter. That means I'm going to divide that by 1,000, 0.500 liters. Okay, temperatures in Kelvin, and I've got my R. So now it's just a matter of plugging things in. Since I'm looking for P, I'm going to divide both sides by V. So I end up with P equals nRT divided by V. Plug in everything I've got. 2.00 moles times by 0.0821 atmospheres times liters divided by mole times Kelvin times by temperature. 290, oh, I get over this side of the board and it does not like to write, sorry. 293 Kelvin. No, that should have been ATM times liters. That's an L. Okay, divided by volume, which is 0.500 liters. Now, before I calculate it out, I go to make sure everything will cancel. Moles cancels with moles. Kelvin cancels with Kelvin. Liter will cancel with liter, and I'm left with atmospheres. Everybody okay with that? Plug it through your calculator. What are we going to get for pressure? Ran out of room on the bottom. And that should have been 0.15 over here. Sorry, I didn't get it written in. I was having a little bit of issue with the pen there. And we got an answer. I hear a lot of calculator buttons being pushed, so hopefully you guys are doing the calculations. I have to work a little bit faster if we're going to make it through today. Anybody got it? Waiting for you. Yes, sorry. 96. Don't think it should be that high, but we might. 0.87. Anybody else got that? Yes. You got it? Okay. It might. It's 27. Okay, that's a very high pressure. That's why I was like, oh, okay. That is extremely high because 1 atmosphere is standard. So you can say this is under a lot of pressure. We would be squashed. Okay, next one. Volume of hydrogen gas. So we're looking for volume this time. If the cylinder has this many moles, again, what does that tell me? Whoops. That tells me I'm going to be using PervNerd again. Because usually it won't say moles unless I'm using the ideal gas law. Exerts a pressure of 3.00 atmosphere. So far I'm in the units that I need for R. And a temperature of 10.0 degrees Celsius. Again, add 273.15 right away before you forget that it has to be in Kelvin. We still have our R. Okay, and we're solving for V this time, so we're going to divide both sides by P. So volume equals nRT divided by P, going through 0.525 moles times by 0.0821 atmospheres times liters divided by mole times Kelvin times by temperature 283.15 Kelvin divided by pressure, which is 3.00 atm. Again, stop, make sure things will cancel. Mole, mole, Kelvin, Kelvin, atmospheres, atmospheres. Does it make sense that volume would be in liters? Yes, it does. Yes.
I'm not getting why you do atm times liters divided by 1.
That's the unit on R. That's the whole unit on R.
So then what's the 0.08?
That's the number.
Oh, so you times it by...
But that's the unit. That whole thing's like, instead of saying meters per second, it's atmospheres times liters divided by moles Kelvin.
Okay, so you're not actually timesing 0.0821 times 6.
No, it's just the unit on it.
Okay, so it's not...
It is really important because it tells you what units the rest of them need to be in.
Yeah, but like in terms of doing your like timesing things through.
Timesing things through, I'm just canceling units. It's like factor label. I'm keeping track of the units. Yes? 6. We'll take 3. Do I have a second on that answer? Yes, I see. Okay, so moving forward. We got another one, temperature in degrees Celsius. So this time we want temperature, but we want it in degrees Celsius. So I'm going to have to calculate it for Kelvin and then subtract the 273. Okay, so it has a volume of 2.50 liters, this temperature one, volume one. It has a pressure of 300 point torr and contains, this one right here tells me I'm going to be in PervNerd still. Okay,
It's gonna be a perfect.
I got moles. They gave me moles.
If it has
Yeah, and I'm only got one of everything else, right? So if I have Boyles or Charles or combined or any of the others, I'm going to have 2 of something, and I don't. So that tells me I'm going to have R, and R again has that specific unit, so I've got to make sure that everything is in those units. So my pressure is not in the correct units, it's in torr and not in atmospheres. So I need to switch that. So there is 1 atmosphere for 760 torr. So we have to divide that so the torr will cancel. So it'll be 0.3 or 4. Somebody do that real quick for me. 300 divided by 760.
The
Yeah.
gas constant, is it always going to be ATM over there?
Yeah, it's always going to be this unit and always this number.
So you always don't want to change the pressure back to it.
Right. This is the only gas law that other things besides temperature have to be in specific units. Okay? Yes.
So you need an ATM in each Pervner equation.
Right. This is why these units are so important on R, because it tells me exactly what each of those have to be in.
So how do you know that you need the torr to ATM?
Because they gave me torr, and I can't use torr. I've got to have it in ATM.
Because torr is.
Torr isn't in part of my R, and my R is my constant. And since it's not in my units on my constant, I need to be able to cancel it out.
So the units on R tell you what units you can use in the entire equation.
Right, for Pervner.
Okay.
Only for Pervner. All the others I can use torr or whatever I have as long as they're the same because they'll cancel. Okay, so somebody got this one for me? Yes. 0.39. Okay, and that would be ATM. So this time we're looking for temperature over here. So I'm going to divide both sides by NR, right? So temperature is going to equal PV divided by NR. Everybody okay with that? Are we okay? All right, let's plug in. That point all you have to do is plug in. So 0.39 ATM times by volume 2.50 liters divided by N 0.100 moles times by R atmospheres times liters divided by mole times Kelvin. Checking to make sure the units cancel and give me what I want. I want temperature, so moles cancel, ATMs cancel, liters cancel, and I've got 1 over Kelvin, which Kelvin will flip to the top. Okay, so remember when you have more than one thing on the bottom, when you hit the divide sign, you need the parentheses around, times through, close the parentheses, then hit the equal. See what we get.
Is there a way in Pervner that ATM could be times torr so that torr could be used, or is it
No.
always just torr?
It'll just be those 4 units. Don't try and get into a different unit, or you're going to end up messing. You could theoretically, yes, but it's going to cause you more problems.
So you just always want to.
Yep.
And why did you divide by hand?
Because I'm trying to get T by itself.
Oh, okay.
Because I'm solving for temperature, which I don't have. Okay, anybody got the answer? Yes. 0.8821. I cannot write today. And that's Kelvin, right? Did anybody else get that? No, we got shaking heads. What did we get? Give me another one. What did you get? Yes. 1.120. Like this? 120.1. Okay. Do I have a second on this one? No. 118. Boy, we're having a hard time today. Do I have a second on 118? Oh, we got a number that we could. Okay, so that's Kelvin. They wanted Celsius. What do I have to do to go from Kelvin to Celsius?
Minus 273.
Okay, so I'm going to now take a minus 273.15, don't forget the 15, to get to my degrees Celsius. Okay, what do we get? Negative. Okay, and since we only have 3 significant figures, we'll just go with that. Okay.
What the test is going to be just like first.
A lot of, yes. Okay, going forward. We okay? Sorry, my back is bugging me and it's making my leg go numb. So, okay, so going forward. Oh, yeah. We have 2 grams. 2 grams would be used for what? Oh, I don't know. I'm just going to bring it down. Okay, a sample of gas has a volume of 1.12 grams, 1 liters. That would make more sense. At STP. What was STP? Standard temperature and pressure. So what was standard temperature in Kelvin? 273.15 K. What was standard pressure? 1 atmosphere. Good. Okay. Calculate its molecular weight. Ooh, molecular weight. What is molecular weight? How many grams are in a mole, right? When we add up the molecular weight, we're looking at grams per mole, right? Okay, so, and this was grams up here. And identify it as helium, neon, or argon. All right, guys, what law am I going to use? Is it Pervnert? Can I use Pervnert here? Yeah, I can use Pervnert here. So I'm going to be looking for N, because N is the number of moles, right? If molecular weight is grams divided by moles, and they gave me grams, I should be able to do grams divided by moles if I've got moles, right? Okay, and I do still have R, right? Okay, so this time I'm looking for N, PV equals nRT, so divide both sides by RT, right? So then we've got N is equal to PV divided by RT. Plugging in, we've got 1 ATM times 1.12 liters divided by 0.0821 atmospheres times liters divided by mole times Kelvin times by 273.15 Kelvin on the bottom. Going through and double checking that units cancel and give me what I want. Oops. Nope. Sorry. Ignore this one. Ignore this one right here. I oopsed. Okay, L and atmosphere, I should get moles. Okay, remember when you hit the divide sign, parentheses, close parentheses over here, and then hit your equal, what did we get for N?
Oh, because you're looking for N, so you're dividing R.
Yep. So I'm trying to find this one, so I got to get it all by itself. I need to isolate it. Okay?
So STP, is that the same?
Standard temperature and standard pressure. So 1 atmosphere or 760 millimeters mercury or 760 torr or 101 point, whatever I need. The R is always a constant. I have to remember it. Memorize it. Yep.
So the original equation is PV equals nRT. So why is there 1 ATM and 1.12 liters? Yeah, that's the P and the V, but like, why would that be on the other side? Oh, you just...
I solved for it. It's on top.
Okay, so you're not doing anything with the equal on the other side of the equals.
I'm just getting N by itself. I'm just doing math. I'm just finding N by itself. So to get N by itself, I've got to divide both sides by RT. Over here, the RT would cancel out, and it would be over here. Okay? All right, so anybody got N for me? Anybody got, yes, what is it? 0.049 moles. Okay, so I know molecular weight is grams divided by moles, right? So I have 2 grams, so my molecular weight is grams divided by moles. So plugging in 2.00 grams divided by 0.049 moles, what is my molecular weight? .81 grams per mole. Which of these has that mass or close to it? Argon. Woohoo! It's 39, right? So 40.81, if I'm doing calculations that I'm off a little bit. It's okay. That's the closest one, so I would say it's argon. Okay? We okay with this so far? Thumbs up, yes?
Where does the K cross out with the top?
The K comes off right here with this. Is that what you mean?
Yeah, I just saw that come.
Well, it's on the top. This is on the bottom, on the bottom. So this is just on the bottom. So this is like on top of that. Okay? All right, going forward. Oh my goodness, look at this one. A still container contains a mixture. Like I said, I'm a visual person, so here's my still container. I'm not a very visual drawer. I'm not an artist. Okay, it contains a mixture of nitrogen, oxygen, and carbon dioxide. The total pressure, PT, in the tank is 2,100 torr. The pressure exerted by nitrogen, PN2, and oxygen, let's see, is 810 torr, and P of oxygen is 920 torr, respectively. What is the partial pressure of carbon dioxide? Okay, this is whose law? Whose law? Dalton's. Okay, so pressure total is equal to all the little parts added up, right? Okay, so pressure total here is going to equal the pressure of nitrogen gas plus the pressure of oxygen gas plus the pressure of CO2 gas. Okay, so pressure total was 2,100 torr is equal to 810 torr plus 920 torr plus pressure of CO2. Solve for pressure of CO2.
Oh, wait, so PT, okay. Oh. Well, that's easy. You just do the 2 minus the 1.
370. I've got a P CO2 as 370. Do I have a second? I didn't hear. Did we have a second? Yes. So pretty easy, right? This helps me by visualizing what's going on. If it helps you, great. If it doesn't and you can do it without, that's fine too. All right, so that's a duh law. Okay, now we're doing another one. All right, going back through. A 250 milliliter sample, that's the first volume I come to, of oxygen gas. It's collected by water displacement. Okay, we did this in lab. As a result, oxygen is saturated with water vapor. So I'm thinking, okay, I've collected this, it's bubbled up through, I've got pressure of H2O, and I've got pressure of O2 up here underneath the water. Okay? Like I said, I'm a visual person. The partial pressure of the water vapor at the preliminary temperature is pressure of the water is 22 torr. Calculate the partial pressure of oxygen, so we're looking for P of oxygen, if the total pressure is 720 torr. Oh, we should be able to do this, right? What's the equation we're using? Again. Dalton's duh law, right? So the pressure total is equal to the pressure of H2O plus the pressure of O2. And if we're looking for O2, pressure of O2 is equal to pressure total minus the pressure of H2O, which would be 250, nope, try again, 720 torr minus 22 torr, and I'm running off the board here, and we get 698 torr, right? I don't want to lean over. Right? Everybody okay with that? Nope. Yep. Everybody okay? So all I did was just take the pressure total minus the pressure of the water, because Dalton's law says the pressures have to add up to give me the pressure total, right? Okay? All right, going forward. Oh, compare the mass of bromine molecule. The mass of a bromine molecule, so Br2 is 160U. And the mass of an argon molecule is 40U. Compare the rates at which these gases will diffuse. Whose law? We did this one last time. It's Grandma's law, right? Grandma's law. So rate A divided by rate B equals the square root of the mass of B divided by the mass of A. So the mass, we usually call these A, the first one they talk to, and the second one would be B. Okay? So the rate A to B, relative rate, this is also known as relative rate, which is that fraction, okay, is equal to square root. Mass of B was 40U. Mass of A was 160U. The U's cancel. And this becomes square root of 1/4, right? Which is should be 0.25. Because this becomes 1/2. 0.25?
No, well, the square root is 45, right? Because 1/4 is 0.25, and then the square root is.
Okay, 0.5. Sir, I don't have my calculator on top of me, so I will believe you. Do I have a second on that one? Okay, awesome. So this is the relative rate. Notice it doesn't have any units because the units would cancel. Okay, yes? That's just the law. This is Graham's law. It switches. So just remember, if it's on the top for the rate, it's on the bottom for the mass. It just flips. Okay? All right, going to another one. What?
Wait, so so 0.5 was rate 8.
No units. No units. It is the relative rate.
Wait, so then what is rate A and rate B?
So sometimes we're solving for one of these. But if we're not solving for one of these, what we're solving for is the relative rate. How fast is one compared to the other?
Okay, so if you're trying to find rate A, you would times by rate B.
Right, when it was done, I would times by rate B, and it would have a unit. Okay, like meters per second or whatever. Okay, all right, so let's go to this one. Which will diffuse faster? Who's law again? Whenever it says diffuse, same one. So rate A divided by rate B equals square root mass of B divided by mass of A. Okay, which will diffuse faster? This becomes A. First one that I talk about is A. Second one I talk about is B. What do I know about this? They didn't give me any numbers. They're masses. So the mass of A is what? So that's helium. 4.026. 0.026. Okay, and the mass of neon becomes mass B, which is 20.180. Okay. All right, so plugging in, we got a relative rate, right, because that's what we're solving for here, because it wants a relative rate, is equal to square root of B, 20.180, divided by A. Now, you'll notice what I did. I could have just taken and tried to put it in right away, but I purposely wrote this out because what I see is the biggest mistake for kids is they try and do this in their head and they forget that it flips. Okay, they forget that the equation flips. So you need to make sure you write it out, write the equation out, identify each one, and then put it in, and you won't screw up. Okay?
Rate A is always the one that comes first.
Yeah, whatever they talk about first is my A. Whatever they talk about second is my B.
But then when it goes to the final,
It's still A and B, but rate A over rate B gives me the square root of mass B over mass A. So they flip on this side. B becomes on top. Just the way it is. Okay, what do we get for this answer right here? Square root of 20 divided by 4. Square root of about 5. 2.25. Okay, do I have a second on that one? Okay, again, no units. No units. Okay? All right, got a riddle for you. Okay? I've got a thing here that I can connect two balloons with. I'm going to blow balloon A up. And I'm going to deflate balloon A. Okay. I'm going to do the same thing with B. A does not like me. I need 2 people to come help me. Can I have 2 people come up and help me? 1, Kelsey. Somebody else, Ryan. You were volunteering. Somebody else. Come on up, Ryan. You go grab that one. Okay. I'm going to have you hold that one. We hold this while I try and get it on. Okay, I want you to hold that one on. Okay, so we've got 2 balloons here. One is more inflated than the other one, right? So up here the riddle is, if I open these up and I have these guys massage this, to get things moving, is this big one going to get bigger? Or is this small one going to get bigger? Or is this going to get smaller and this is going to get bigger? What do you think? So looking at A, do you think that the big one's going to get small and the other one's going to get big? Anybody believe that? Okay, how about B? They'll both end up the same size. Raise your hand if you think that. Come on. Commit, commit, commit. Okay, what about C? That this is going to get bigger and this one's going to get smaller. Anybody believe that one? So it looks like most people believe B, right? No? A? Okay, so A, B, or C? Hold it up. A, B, or C? A, B, or C? Okay, got it? Okay, hold it on and with the other hand, ready? Go.
We're supposed to touch it?
Yeah, I want you to touch it and push it. Who's going to win? Who's going to win? Who's going to win?
Oh, okay.
Come on, Ryan.
I'm trying.
Come on.
Blowing air in.
I feel like I have air coming out of mine. That's what I guessed.
Okay, so the small one actually got smaller. Why? Why would that happen? Okay, let go of them. Let's see. They're not doing anything. It's not blowing it back up. Why? Why didn't it go be equal? Did you really try, Ryan?
Yeah, I did.
Are you sure?
I'm positive.
See, this is just.
You're just really strong, right?
This is just my thought.
Okay.
Because this one, the balloon is thicker, so I feel like it's gonna.
So the pressure on the air inside is stronger. Have any of you ever blown up a balloon? When is it the hardest to blow it up? Very first. Thank you for your help. So it's really hard at the very beginning. That's because the pressure outside is stronger than the pressure of the air inside. So once this got blown up a little bit, after you get a balloon started, is it easier to blow it up? Oh yeah, it's a lot easier to blow it up once you got that first initial pop in there, right? So this is what's going on here, is we're actually looking at the pressure inside and outside of the balloon. Okay, so how much pressure is exerted by the outside forces versus how much is pressured by the inside? Okay. When a balloon is being filled, the pressure inside has to be bigger than the pressure outside in order to fill it. Okay? When a balloon is filled and tied, the pressure outside and inside are equal. So that's when we moved the burette last time and we moved it into the graduated cylinder and we got it equal so we could read it. We were equalizing the pressure outside the burette and the inside because we knew what the reading of the outside was, but we didn't have a pressure reading for inside the burette until we equalized it, and then it was the same as outside. Okay? When we deflate, the pressure outside is greater than the pressure inside. Okay? All right, so that's our little demo here. So we're going to be talking about changes of state. I'm trying to get to where we need to get to. You guys have known this for forever. If I have a solid and I melt it, I get a liquid. If I heat it more, I get evaporation. And then if I cool a gas, I'm going to get a solid again, if I cool it really fast. Okay, if I go the other way, I can sublime a solid to a liquid. If I heat it really fast, it will go directly into a gas. I can condense it and I can freeze it. So this is sort of our triangle of heat. Okay, and that's what those triangles down at the bottom of your page are. So if you don't know what they're there for, that's what they're there for. So you know what they are. So we've got a solid and going back and forth depending on if we're increasing heat or decreasing heat, we either freeze or melt between a solid and liquid. From a solid to a gas, same thing. We've got what's called sublimation and deposition. These are probably words you haven't heard before. You might have heard sublimation, but not deposition. Sublimation is when I go from a solid directly to a gas. Deposition when I go from a gas directly to a solid. This happens when we make dry ice. We take carbon dioxide gas, we cool it down real fast, and it makes a solid, which is dry ice. And if you watch dry ice, as it heats up, it goes directly from a solid to a gas. We don't have a liquid CO2 in between. Okay? If I go from a gas to a liquid, then I have what's known as condensation. If I go from a liquid to a gas, that's what's known as evaporation. So we need to be familiar with these words. So if I say this substance goes through deposition, what am I talking about in phases? Gas to solid. If I say this substance undergoes boiling, okay, it would be, boiling would be melting to, or sorry, boiling would be liquid to a gas, you're right. Okay, so we need to go back and forth. The red ones are what known as endothermic processes, meaning I'm putting heat in to change it. Exothermic processes would be represented by the blue arrows. So exothermic process, I'm taking heat out, yes.
Isn't there technically nothing as a gas to a solid in a split second and turns to a solid? Like
no, there's actually things that go directly from solid to a gas.
Like no liquid ever.
Right. CO2 is one of them. I have to actually get things manipulated with pressure and temperature exactly right to actually get liquid CO2. Okay? All right, so let's do this really quickly. Let's determine if each of these are exo or endothermic really fast. Condensation, exo or endo, going from a gas to a liquid, condensation. Exo, I'm getting rid of it. Okay, what about boiling? Endo, good. Okay, what about sublimation? Sublimation is going from a solid to a gas. Solid to a gas. Endo, I have to put heat into it, right? Energy into it. Liquefaction. Exo. If I'm liquefying something, that it infers that I'm taking a solid and making it a liquid. So liquefaction basically is solid to a liquid. What about freezing? Liquid to a solid. Exo. And vaporization. Liquid. Okay. So they should be very easy for you to do, I'm hoping. And these were actually right here. Okay. So any questions with this? Fairly simple, right? Okay, going forward. When we talk about going from a liquid to a gas, if I'm in a closed container, we have what's known as vapor pressure. That's at the point at which so much gets up here that some of it starts going back. If I have an open container, we just call it evaporation, and after a while, the level of the liquid gets lower and lower and lower. But if I have it in a closed container, like a terrarium, that liquid, after a while, comes back down as rain and gets back in the soil and comes back up and goes back down and comes back up and goes back down. So we have a process going there. This is known as vapor pressure. How much pressure do I have? Okay, so let's define some of these things for us. So evaporation or vaporization is an endothermic process of going from a liquid to a gas. What do evaporating molecules always carry away from a liquid? Kinetic energy or energy. So as they leave, they're taking energy with them, and what's left behind is cooling. What happens to the remaining liquid? It becomes cooler. The process above is called evaporation or vaporization. Condensation is the opposite. It's an exothermic process where a gas gives up energy and is changed back into a liquid or a solid. Vapor pressure, again, we talked about this in the last slide, is the pressure exerted by a vapor above a liquid, but it's usually on a closed system. Okay, and what type of molecules tend to have higher vapor pressures? Polar or nonpolar? It's nonpolar, because polar molecules will tend to stay in liquid and don't like to go to vapor very often. Okay, nonpolar molecules aren't attracted to each other. So if we remember our kinetic rules, the ideal gases are nonpolar, and because they're nonpolar, they are not attracted or repelled. And because they're not attracted or repelled, they can go into vapor easier and get out of solid and liquid states. Okay, give you a minute, I can see the bob and weave going on. Okay, bob and weave looks like it stopped. It's going forward. No, still bobbing and weaving. Okay, just not on the back row. Back row's got it. Okay, going forward. So if you've ever taken and put alcohol on your hand or your face or whatever, it feels cold to the touch, right? After a while, it gives you that cold feeling as it evaporates off. So if we were put two different kinds of alcohol, this would be ethanol, like a drinking alcohol, and this would be butanol, a little bit heavy, although I probably wouldn't put butanol on my skin because butane is used in, or is a smell of, okay, barf. Okay, it's a smell of barf. I wouldn't want it on my hand. Okay, it's a longer molecule. How would I tell which one would be, which would go to gas faster? They're both alcohols, so that's going to be the same. Thinking of Graham's law, which one moves faster? Something that's heavier or something that's lighter? Lighter. Lighter will move faster. So looking at this, I've got 2 carbons versus 4 carbons, 6 hydrogens versus 10 hydrogens. Which one's going to be lighter?
Left.
So the left hand, right? So it's going to feel cooler because it has a lighter, a smaller molecular mass. And you can do that with any compound. We actually do in 1120, we get to a lab where you're actually doing the vapor, finding out what the temperature is of different alcohols as they evaporate from thermometers. Okay, so let's talk about sublimation and melting. Sublimation, again, is an endothermic process where we change directly from a solid to a gas without becoming a liquid. Melting point is where we have a solid changing to a liquid. I know I'm giving you a lot of vocabulary here, but we'll get to a point where we need it. Decomposition is when I have a chemical change that results from heating. So if I heat something, it becomes something new that we have a decomposition. And what are 3 substances that sublime? You do need to know these. Dry ice, CO2, water will sublime, and iodine. Water will sublime? Wait a minute. Have you ever had ice in the freezer for a long time? What happens to it? If ice is in the freezer for a long time, it can crack, but if you have it in ice trays, I know a lot of you don't even know what ice trays are. Ice cube trays, for a long time, they'll actually start to shrink. And that's because it will go directly from a solid to a gas. Okay, so 3 things, 3 common substances sublime. Dry ice, which is solid CO2, water, freezed and dried. So if it's in my freezer, okay, and iodine. We okay to go forward? No. Okay.
What type of reaction is
Melting point is a point at which a substance changes from a liquid, solid to a liquid. That's it. Yeah. Okay, we okay to go forward? Last one, just remember, dry ice, solid CO2, water, freezed and dried. So it has to be in a dry environment. If it's in a wet environment, it won't work. And iodine. Okay, so here we have this lovely thing. This is called a phase diagram. This phase diagram you need to be able to read. You need to be able to do things with. This also is on most of ACTs, SATs. They use graphs. You need to be able to read graphs. Okay, going along the bottom is my temperature. Going along the top is pressure. Every compound, every element has its own phase diagram. Okay, it is basically a map of that chemical. At what pressure and temperature? Is it a solid, liquid, gas? Where does it undergo boiling? When does it undergo freezing? When is it sublimation? So this point up until what we call the triple point, this is a point at which it goes directly from a solid to a gas. That's where sublimation and deposition occur. The point up from that triple point is the point where I'm going from a solid to a liquid. That's where I'm melting and freezing and melting and freezing. That's my melting and freezing line. Triple point is where I can have gas, liquid, and solid of the same compound all existing at the same time. So basically I could take water, ice water, and boil it if I've got the right temperature and the right pressure. Yeah, so I can have ice water here boiling, and I'll give gas. Okay, this line right here is my boiling point. Okay, or my evaporation point and my condensation point. These lines represent an equilibrium between phase changes. When we get clear out here, this is the critical point. Past this point, all I have is gas. No matter what pressure I put on it, the temperature is so high, the molecules have so much energy, they can be nothing but gas. Okay? So that's the critical point. So you should be able to read the critical temperature coming down and the critical pressure coming across. The other point that's important is the triple point. So you need to know the temperature and pressure of it. You need to be able to be given any temperature and pressure and a phase diagram and be able to tell me what phase it's in, and if I heat it up, what phases it will go through at that pressure or temperature.
So if you had one at the exact pressure and temperature of the triple point, you consider all three phases?
Yes. You have all three phases present. Like I was saying, you could actually take ice water and boil it, and you would have gas, water, solid water, and liquid water all at the same time. It's really cool to watch. I have to maintain that temperature and that pressure in order for that to happen.
So you'd have to be like boiling water and then like throw ice in it?
No, I have to. Yes, it's not. The ice cubes don't melt. You have solid, liquid, and gas all coexisting at the same temperature. So you have ice water boiling, it gives you off the vapor. And remember, it need to be in a sealed container, so after so much vapor comes in, it would condense back to liquid and solid. So it's really cool to see, but it's one picture in time, one point in time. Okay, so everybody got everything down from the triple point. Okay, so then we go to another diagram. This is called the heat curve. And the heat curve has lots of things that we need to bring down from it. Okay, basically, this right here is where I'm heating a solid in the pink where it has a slope. When I get to this flat point, this is where I'm melting the solid. And then when I get to the yellow and I start having a slope again, this is where I'm heating the liquid. This flat point in the yellow is where my liquid is now changing in where I'm boiling the liquid. Then I get to the gas phase where I'm going up again. That's where I'm heating the gas. Okay, so this flat point here, this first one tells me the melting point temperature. The flat point, the second one, tells me the boiling point temperature. And that flat point, the first one, we have what's called the delta HF, which is the heat of fusion. How much energy does it take to change a solid into a liquid? The second one is the heat of V, or it's the heat of VAP, which is vaporization. How much energy does it take to change that liquid into a gas? So we're going to go a little bit more in depth on this one. We have exact equations that we use at each point. So anytime it's red, okay, where I have a slope on a line, we're going to use the equation Q equals mCp delta T. And I say Cp, it just has C up here. I will always learn that specific heat was Cp. They use C here, whatever. I just learned it Cp. M is mass, Cp is a specific heat for each individual compound has its own specific heat for each phase. So the specific heat for down here at the bottom with the solid area would be the specific heat of the solid. For here it would be the specific heat of the liquid. For here it would be the specific heat of the steam or gas.
So each red line is a different
Cp.
But that's cool. It's
Phase. Yes. So the first one down here from -20 to 0 is a solid. From 0 to 100 is a liquid. From 100 up is a gas. So the blue part is where I'm changing from a solid to a liquid. And because it's a transition, we can't use this equation because there's no change in temperature. So we use this other equation, which is mass times the heat of fusion, or mass times the heat of vaporization. Because we know that it takes energy to change a solid to a liquid and a liquid to a gas. We just can't use a change in temperature to help us figure that out. Okay, this right here, this equation is known as a specific heat equation. And we'll be using it in the lab next week and the week after. Okay. This other one is just a phase change equation. And we'll actually be doing some calculations where we take a solid, like a popsicle, from the freezer, and we heat it up until we get steam, popsicle ice steam. And we find out how much energy that would take to go from that solid in the freezer up to steam at a certain temperature. So we'll be doing that next time. What we're going to do today, in the last 15 minutes, is we're going to do a lab that will find out the heat of fusion of ice. So this is where I'm stopping for today. We're actually going to figure out, for ice, what is the delta H fusion. Okay, and this is the last lab that will go into your lab notebook. Now you'll notice there's just a little, I think there's one page left on your notes. We'll finish that up next time, and then we'll use next time also as a working sapling. Finish your lab notebooks, redo your quizzes, whatever needs to be done after we finish the notes. Okay, so let's go to the lab, and let me explain what you're going to be doing, you and your lab partner. So around the room there are buckets that have ice in them. So what you're going to do is you're going to first, I always get ahead of me. You picked it up last time. If you didn't pick it up last time, it will be in C1110. One person's going to come get a scale. And I don't know if you really need a scale or not. I grabbed them, but I think it does it all through volume. Okay, you'll need a calculator with a temperature probe and an easy link, so you're going to just put those together. You'll need a styrofoam cup that you're going to put everything in. That's going to be our calorimeter. Now it's not going to keep all the heat in, but we'll get close enough. And then you'll need a graduated cylinder. We're going to turn on the faucet over here to hot, and we can use the ones in the lab too, so we're not all standing at one. You need to fill the graduated cylinder. Oh, I know why you guys are all standing there, because we got it after first period. I told you that if you needed it before to come get it. So let me just pass it out. Go ahead and have a seat. I was like, why are you all standing over there? I know, that was really odd. Okay, I'll just pass them down the rows. If we need extras, let me know. I'm going to take one so I can keep track of it. Okay, so over here, what we're going to do is you'll pick up a graduated cylinder and you'll pick up this. Now, let me just say this. Do not do I think it says 80, 70. Don't do 70, do 50. Okay, 50 hot. Change that right now. If you do 70, it's going to be too much and you'll have not enough room in here. So do 50 hot, okay? You put it in here, you get the temperature right away. So don't get your hot until you've got your calculator, your EasyLink, and everything right there. Let me just do this. We'll just bring it up here. Okay, if there's any extras, if you'll send them to the front for me, that would be awesome. Okay, so here's my cup. Okay, I've got my 50 milliliters of water in here. Okay, and it needs to be hot. Okay, so turn the faucets on, leave them on, let people get that last person there at the faucet, turn it off. Then you're going to go get a little cup of ice. Okay, thank you. The little cup of ice. Yeah, I want you to change it to 50. That's what I told you to do. It says 70, change it to 50. Okay, once you get your little thing of ice, and I've got my temperature probe in here that's hooked to my EasyLink, that's hooked to my calculator, that's recording what's going on, right? I've got to write down my initial temperature. Okay, I'm not having to do anything with the computers. I'm just working with my calculator right now. Okay, I'm going to take that ice and I'm going to dump that in. And I'm going to stir, stir, stir. And I'm going to watch until the last of that ice is melted. The minute that last of that ice melts, I need that temperature. Right as that last of the ice melts. That's my final temperature. Then I'm going to very carefully pour the water back into my graduated cylinder. I should get 50 plus a little bit more. So once I get to the 50, I'm going to dump that out. I'm going to put the rest of it in, see how much more I got, and I'm going to put the volume down. Since the volume of water, 1 milliliter equals 1 gram, I can take that as mass. Okay? So that's all I have to do to get that part done. And then I'm going to do some calculations. That's it. Yes?
Initial volume is 50.
Should be 50.00, but don't put it down yet because you're going to write down whatever you get. You might not get 50.00. You might have 48.5. It's okay. Write down what you actually got volume-wise. Okay? Questions? When you're all done, put everything back, get a stamp from me, and you can work on the calculations. Go.